Chapter 13, gases. So the first thing we want to do with gases is define pressure. What can you tell me about a solid? If this is what a gas is up here, uniformly fills container, mixes completely, and exerts pressure on surroundings, what can you tell me about a solid? It keeps its own shape, right? A solid, so the definition of a solid is it keeps its own shape. Whereas a gas, it's uniformly going to fill that container. If we fill a container up, say, with nitrogen, those nitrogen molecules are going to completely fill the container and move around inside. They're not going to be in a single blob of nitrogen. And so mixes completely. If we put two, say, a block of lead and a block of sodium in a container, just one block of each, do those two mix? No, right? It's just two blocks inside of a container. Now, if we put two gases, say nitrogen and oxygen, in a container, they're going to mix completely. Because those nitrogen and those oxygen molecules are moving around in that container constantly. So they're constantly going to be moving and mixing. And finally, the last one is pressure. This is the equation for pressure here. Force divided by area is pressure. So when you're talking about, like, say, PSI, that's pounds per square inch. So that's pounds, your force, divided by an area, inches squared. So this is how we measure pressure. Manometer. We have here is a little gas vessel, little vessel containing some gas here, and some mercury in a tube. What is the pressure? What do we call pressure at sea level? 1, right? 1 atmosphere. At sea level, the pressure is 1 atmosphere. But here in Colorado, are we greater or lower? We're lower, right? Because we're higher up, so we have less air above us, so we have a lower pressure. Now what this does here is this compares the pressure that is inside our vessel to our atmosphere pressure, just pushing down. So on the left side, we have our gas in here, and then we have our atmosphere pressure pushing down. What is the gas inside this vessel more or less than the atmosphere pressure? Good, less. It is less than the atmosphere pressure. Why? Yeah, our atmosphere is pressing down on this mercury, so it causes our mercury on the other side here to go up. And we can calculate this difference in pressure with that H, the height. So if the pressure, like on the right side here, is the pressure inside the vessel greater or less than atmosphere? Yeah, greater. So greater. We have our gas inside the vessel that is pressing our mercury back up towards the atmosphere side. And we can measure this with that difference in height, and usually we measure that in what's called millimeters of mercury. You might see that in a pressure measurement. If there was no difference, we would have mercury right here and mercury right here. And that means your pressure inside the vessel will be the same as the atmosphere pressure. Why do we use mercury? Because mercury, it doesn't want to stick to the glass walls, and it moves very freely at room temperature, and just pretty much at any temperature. It moves very freely. So now Boyles Law, our first law of the gases. Boyles Law. What do you notice? What do you notice about this data table? Okay, so for pressure decreases, volume increases. Good. So actual, what they did is they multiplied this pressure number and this volume number. They multiplied them. What do you notice about all those numbers? Look at the rounded. Yeah, they're all pretty much the same. We have 1.40, 1.41, 1.41, 1.40. They're constant. Even though we're changing the pressure, our volume's changing, but it remains constant, our pressure times volume. So if we look at the picture here on the right, the H, our height, and then the amount of the volume of gas. Now we go to the right here, our volume of gas has decreased, but the height has gotten much larger. But if we were to multiply those together, we would still have a constant number. So Boyles Law, pressure and volume are inversely related. So just like what Dave said, if we decrease volume, we are going to increase pressure. And this is done with a constant temperature and constant number of moles of a gas. So that means if we are moving we're going to decrease that volume, we're doing it at, say, 25 degrees Celsius, and we're always going to use 10 moles of a gas. That remains constant throughout our whole, say, experiment, or how we're altering our gas. So pressure times volume is equal to K, the constant. And we can write it as P1 times V1 equals P2 times V2. Meaning if we have a system at pressure 1 and at volume 1, and they ask us what is the volume at pressure 2, we can solve for V2. So if we look at the picture down here, we have a pressure of 1 atm at 1 liter. Then we move over one container, we have 2 atms, and what's that volume? Half a liter. And then the last one, we have 4 atms, and now we have a fourth of a liter. And if we multiply all those together, do we get a constant number? You can condense a gas into a liquid by decreasing the volume. But here's a good point. Can you ever have zero volume? Why? Because yeah, exactly. If we start with something in our container, we can never have zero volume. Because the smallest we can compress it to is to the exact size of what we just put in our container. So that's important because you're going to be asked to draw some graphs at some point. And it's important you remember that you can never have zero volume. And if we look at each one of these, let's count our particles. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9. We have 9 particles in each container, so we're keeping a constant number of moles of a gas. All right, so try this problem. So we just went over our equation. P1 times V1 equals P2 V2. So what you can do is go through and label this as, here's your P1, here's your V1, and they give you this temperature, but then they say, assuming the temperature stays constant. They just told you the temperature, and they told you it's going to remain constant throughout our experiment, so you don't have to worry about it. And now we can solve, oh look, here's our P2. This is P2. And we can set it up using our equation P1, V1 equals P2, V2, and solve for our V2. It should get 9.88 liters. It's important that we remember our sig figs for this. So make sure you watch your sig figs. All right, so next one. Charles' law. What do you notice about this graph? So as volume increases, temperature is going to increase. So as we increase temperature, these are various gases they list here. As we increase temperature, our volume is going to increase. This is Charles' law. So volume and temperature are directly related. We say they're directly related because if we increase one, we're going to increase the other. Now if they are inversely related, that means we increase one and decrease the other. But temperature and volume are directly related. Now the little kicker here is that this is done under a constant pressure and still a constant number of moles. So that means we are increasing the temperature of our system, but we maintain a constant pressure. But what is very important here is the next line. Because we're dealing with temperature, we need to convert everything to Kelvin. Why? Never goes to zero. That's important. In Kelvin, zero Kelvin is called absolute zero. What happens at absolute zero, at least theoretically? Everything stops. right? Your electrons, they'll stop. It's important. Everything you convert from Celsius, convert it from Celsius to Kelvin. That way we never have a number that is 0 or less than 0. Because here's our equation right here. V1 divided by T1 equal to V2 divided by T2. What would happen if we had a negative temperature? Yeah, we get a negative volume. If we got a negative temperature, we would somehow then get a negative volume. Is that possible? No, right? We already talked about that. You can't have a 0 volume or a negative volume. Now, what if you had a 0 temperature, though? Like, say, 0 degrees Celsius. What is it? Can't divide by 0, so it's undefined. We always convert to Kelvin. Always convert to Kelvin so that we do not have a undefined or a negative volume. So try this sample problem. Try this sample problem. So we have a V1. Here's our first volume. We have a T1. And we have a T2. We need to find our V2. So we have our equation V1, T1, V2, T2. And we just substitute our values into the equation. Just remember, though, remember to convert to Kelvin. If you do not convert to Kelvin, you will get a negative volume in this problem. And we cannot have a negative volume. So make sure you convert, always convert to Kelvin. Because we're going to get, when we start using our gas constants, all those are in Kelvin. We want to make sure our units cancel. Last law, Avogadro's. What do you guys think this relates to? Avogadro's number, which is what?
6.022 times 10.
Yeah, I don't care about the exact number. What does it allow you to do?
Moles or molecules?
Yeah, it lets us count molecules. So what do you notice about these three pictures? Yeah, as our N here increases, our volume increases. So as the number of molecules increases in our system, our volume is going to increase. Tommy, what do you notice about the pressure, though? The pressure is the same in each one. So if we have a constant pressure, what's the only thing else that has to be constant? What is it? Temperature. So here's Avogadro's law. Volume and number of moles are directly related. As we increase the number of moles, we are going to increase our volume. And this is done under a constant temperature and pressure. So here's our equation. N1 divided by V1 equals N2 divided by V2. Now next time, though, we're going to get into combining all of them to form one sort of combined gas law. If you start putting more stuff in a container, you're going to eventually start needing a bigger container, right?
What's N?
N is the number of moles. N is equal to number of moles, while V is equal to volume. Here's a sample problem. Give this a try. So the correct answer is 76.3. Now, since these are proportions, right? We don't have to go N1 divided by V1 equals N2 divided by V2. We could do what's up here. V1 divided by N1 equals V2 divided by N2. Because in this way, we have our unknown variable, V2, in the numerator. You still can do it as N1 divided by V1 equals N2 divided by V2, but you need to remember that your unknown would be in the denominator. Because otherwise you're going to get a very small number. What does it turn out to be like, Vaughn? 0.013, because your answer is 0.013 equals 1 over x. And you want to solve for x, where x is our V2. That's like if I write it like this, 1/2 is equal to 1/2. Is that true? Now if I say 2 over 1, is that equal to 2 over 1? Yeah. Right? They're still both true. So you can still flip them. Just make sure you remember to flip both, not just one.